My name is Hao Zhang. I'll introduce the paper submitted to IMETA. The title is Prophylactic Supplementation with Bifidobacterium infantis, or its metabolite inosine, attenuates cardiac ischemia reperfusion injury. Recent studies highlight the important connection between the gut microbiome and various cardiovascular diseases, including hypertension, heart failure, and myocardial infarction. The gut microbiome produces metabolites that impact immune and inflammatory responses, influencing the development of these conditions. B. infantis, a common probiotic, can protect against infections and reduce inflammation in various gastrointestinal and non-gastrointestinal disorders. However, it remains unclear whether B. infantis may affect the prognosis of CAD, particularly in the context of myocardial IR injury. Here, we demonstrated that B. infantis and its metabolite inosine had protective effects on heart injury against IR through anti-inflammatory effect on immune cells and functioning as an alternative energy source to alleviate cardiac cell death following IR. Here is an overview of our study. We demonstrates the prophylactic potential of B. infantis and its metabolite inosine in mitigating IR injury after acute MI. First, we investigated the potential of B. infantis gavage in protecting the heart from IR in mice. After depleting gut microbiota, mice were given B. infantis or PBS for 7 days, and then underwent IR surgery. 7 days after surgery, there was a noticeable increase in heart size in mice that had undergone IR in PBS group compared to sham group. This increase was reduced by B. infantis gavage. B. infantis gavaged IR mice had better heart function than PBS gavaged IR mice at 1 and 2 weeks post-surgery. These results demonstrate that the gavage of B. infantis plays a role in the prevention of left ventricular dilatation and the preservation of cardiac function following IR. Histopathologic examination of tissues from B. infantis to gavaged and PBS gavaged mice after IR showed larger scars and more fibrotic tissues in PBS gavaged mice, but these were significantly reduced in the B. infantis gavaged mice. In addition, gavage of B. infantis reduced cardiac cell death and decreased levels of cardiac troponin T in mice after IR injury. Together, these results further prove that B. infantis exerts a cardioprotective effect through the reduction of IR-induced cardiac fibrosis and cell death. Previous studies reported extensive inosine production and secretion by B. infantis. We postulated that inosine may play a role in the cardioprotective effect of the gavage of B. infantis. We compared inosine levels in mice given B. infantis versus PBS and found higher levels in B. infantis treated mice and found that inosine injection mimicked the positive effects of B. infantis gavage in mice, reducing cardiac hypertrophy and serum CTNT levels after IR. In addition, inosine improved heart function after IR and reduced fibrosis in the heart, similar to the effects of B. infantis. These data suggest that inosine recapitulates the cardioprotective effects of B. infantis after IR. To better understand the mechanism underlying the protection of inosine treatment against cardiac IR injury, we performed a transcriptional analysis of infarcted heart tissues of the inosine-treated IR group and PBS-treated IR group 1 day after IR, along with the heart tissues of the sham group by RNA sequencing. Go-analysis showed that inosine reverses adverse metabolic changes caused by IR by upregulating pathways associated with fatty acid catabolism and improving impaired cardiac energy metabolism. Conversely, inosine treatment downregulated 9 out of 10 pathways associated with inflammation, suggesting an anti-inflammatory cardioprotective effect. Additionally, inosine treatment rescued the upregulation of cytokine production and apoptosis after IR. Therefore, our transcriptional data suggests that inosine confers cardioprotection by the improvement of energy metabolism, as well as the attenuation of cardiac inflammation and cell apoptosis. In accordance with the results of transcriptome analysis, we found that inosine treatment have anti-inflammatory effects, as shown by reduced levels of TNF and interleukin-1 beta following ischemia reperfusion injury. To better understand how inosine treatment mitigated the IR-induced inflammation, we performed a flow cytometry analysis of the immune cells in mouse hearts after IR. We found that inosine decreased DC and NK cells 7 days after IR, suggesting its anti-inflammatory role after cardiac IR. Previous studies have shown that inosine exerts anti-inflammatory and immunomodulatory effects through adenosine receptors, and our results confirm this by showing that blocking this pathway prevented the cardioprotective effects of inosine in hearts undergoing ischemia reperfusion. Another way, inosine treatment was reduced tunnel positive, denoted cardiac cell death after IR. And in vitro study showed that inosine conveyed a dose-dependent anti-apoptotic effect in C2C12-OGDAR model, and this effect could be blocked by inhibitor of PNP. Prior studies showed that inosine can contribute to ADP recovery through the purine salvage pathway. Indeed, we found that knockdown of APRT or HPRT1 eliminated inosine's protective effects. Consistently, adding inosine increased AMP levels in C2C12 under OGDR, leading to higher ADP levels. Finally, in vivo study showed inosine treatment increased ADP levels in IR mouse hearts at 30 minutes and 24h post-reperfusion, showing improved energy metabolism. Taken together, these data suggest that inosine attenuates cardiac cell death by serving as an alternative fuel source in mouse hearts upon IR. Our study demonstrates the prophylactic capabilities of B. infantis and its metabolite inosine in reducing IR injury through anti-inflammatory properties and serves as a substitute energy, highlighting the potential translational use of B. infantis and inosine in preventing and potentially treating myocardial IR injury.